Hello students, this is Faizan Mirza. We are discussing chi-squared test today. Chi-squared test, this is denoted by this symbol chi-squared, and this is a statistical test which is used on discontinuous data. It is used for evaluating whether the difference between the observed and the expected values is significant or not. It can be applied in various examples. One of the example is its use in genetics. For example, if 144 offspring were produced when two plants heterozygous for both traits were crossed with each other, and you have a plant AADD purple cut and another AADD purple cut, these were produced by sibling crosses of homozygous recessive and homozygous dominant for the two traits which have been discussed previously. So you are taking two heterozygotes and two hybrids and for both the traits and you're crossing them together. So 144 offspring were produced here. You expect the ratio to be 9331. We get four phenotypes here: purple cut, purple potato, green cut, and green potato. I have skipped the stem and the leaf in speaking. So the observed values of these 144 offsprings included 86 were purple cut, 26 were purple potato, and 24 were cut leaf with green stem, and 8 were green potato. These are the observed values of the 144. You just have these organisms growing, and then you count them, and when you counted them, this is what you came out to be. These values came out to be. Your expected ratio was 9 is to 3 is to 3 is to 1 for such a cross. And when you add the value of 9331 together, you get 16. So for our expected values, we'll calculate uh, this 144 offspring with the ratio of 9331 using the 16 value. So what are we doing here? We calculate our expected value in such a way that our expected values for the first phenotype is 9 upon 16 multiplied by 144, which is the total number of offspring produced. We expected them to be 9 out of 16, so the value comes out to be 81. We divided 3 by 16 and multiply them by 144, we get 27. And 3 by 16 for the next phenotype by multiplied with 144 again. The last phenotype 1 upon 16, we expected it to be 1 out of 16. And this is again multiplied by 144. Our expected values come out to be 81, 27, 27, 9 respectively. So our observed value for the first phenotype was 86, but we ended up with 81. Our first value for the observed is different. So is this significantly different or not? And just compare 26 for 27, 24 and 27, 8 and 9. There is a difference. So the difference is there between observed and expected. But is this difference significant or not? This is the big question. So this is where chi-square test comes in. What I told you, chi-square test is it used on discontinuous data and used for evaluating the difference between observed and expected values, whether it's significant or not. So what do you do now? You go and make a table. You have to just mention the categories first, then the observed values in the next column, the expected values. You just subtract O minus E. You apply this symbol calculation here. You subtract E from O. You make sure that the signs have been added. You square the values there, and when you square them, basically the sign gets removed. The negative sign gets removed. That's why the signs are important here. So you get the values of O minus E squared, and then the last column, you sum up these values. The summed value, this 25 for the first row will be divided by 81. The value 1 will be divided by 27, 9 by 27, and 1 by 9. These are the expected values for each. So you just divide them. And when you divide them, you get your last column filled. You fill these up with two decimal places. So this is 0.31, 0.04, 0.33, 0.11. What do you do? This is the formula for chi-squared. Chi-squared is equals to summation of O minus E squared upon E. How do you solve this formula? This is why we did this table. In statistics, we perform these. We fill up the value in the table, then we get the values of our formula. So the last column here, if you sum up all these values together, this is the answer that I'm getting 0.79. So this is the summation of the last column. This is exactly what the formula states, summation of this value. And this value is given in this column. So yeah, this is 0.079. So 0.79 is my, sorry, 0.79 is my chi-squared value here. So now I have to interpret this value. So to interpret this value, I'll compare this against a critical value. And for critical value, we use a table which is for chi-squared. So this is the table given for chi-squared values. This is the table given in books for regarding biostatistics. So this is the table of chi-squared values. The degrees of freedom are mentioned on the left. The probability greater than 0.1, 0.05, 0.01, and 0.001 are mentioned at the top. In biological experiments, we prefer to use 0.05. Why? Because p less than 0.05 or probability greater than 0.05 basically means the same thing. So this value and probability greater than 0.05 basically means the same thing. And what do they mean? They mean 95% confidence. They mean 1 in 20 chance or 5% chance of error. So whatever your conclusion will be from this experiment, whether you state that the difference is significant or you say the difference between observed and expected is not significant, you are just giving the answer with 95% confidence. You are leaving 5% chance of error. You are leaving 1 in 20 chance of error. What do you mean by 1 in 20 chance of error? That if you repeat the experiment, for example, 19 times, in 20 times, so in 19 of those 20 times, you'll get the same outcome. But yes, in one, you can get a different conclusion, and that's perfectly acceptable because this is what we actually predicted. So we'll use this column. Otherwise, until unless it's stated otherwise, this is where we use. I took this table from Mary Jones' fourth edition, which is given on page number 387 in your book. Um, the second thing is to calculate the degree of freedom. The degrees of freedom is calculated using the formula in chi-squared. Degrees of freedom is equal to the number of categories minus one. Since we had four categories, which four categories we had? We had four phenotypes: purple stem cut leaf, purple stem potato leaf, green stem cut leaf, and green stem potato leaf. So these were the four values, the four categories here. So this is the number of categories, four. I subtract it with one. So I am subtracting the value of one from four. My answer comes out to be three. So what I do, using this particular with this particular chart here, what I'll do now, I'll just go straight in the table, straight in the row of three. So when I go straight in the row of three and I come down in the column of 0.05, my value comes out to be 7.82. So what I'll do, I'll just compare my chi-squared value of 0.79 with the critical value 7.82. Now, since my 0.79 chi-squared value was less than the critical value is 7.82. So the difference between the observed and expected is not significant, and it is merely due to chance. And there is 1 in 20 chance of error, 95% confidence, because we use CP less than 0.05. So whenever we are using chi-squared, or when we're using a statistical test such as this is the conclusion that we actually are aiming at. Chi-squared, if it's less than the critical value, the difference between observed and expected is not significant. It is due to chance, 1 in 20 chance of error, because P is less than 0.05. If the chi-squared value is greater than the critical value, the difference between observed and expected is significant and not due to chance, but due to some other factor. And again, there will be 1 in 20 chance of error. So this is what chi-square test is all about. That's it. Thank you so much.